So in the H1 reflections problems, we are focused primarily on the basics of confidence intervals, and we're also going to do some spiral review of standard deviation and variance, which I know you love, and the sampling methods and things. So here we go. Problem 1. A New York Times CBS News poll asked a random sample of U.S. adults the question, do you favor an amendment to the Constitution that would permit organized prayer in public schools? Based on this poll, the 95% confidence interval for the population proportion who favors such an amendment is 0.63 to 0.69. And then they ask us to interpret the confidence interval. When you're interpreting the confidence interval, all right, then there is on page 2 of your H1 notes, the blurb. This is what you pretty much do. You fill in this template. So our confidence level was 95%. So we are 95% confident. Okay, so it's probably C or D. That the interval include your lower limit and your upper limit. So it has to have 0.63 to 0.69. Captures the, and parameter is the true value, in this case, the true proportion. So you can see there's a difference. Let me go ahead and get my little laser pointer. There's a difference between C and P on that point. Here it says the true proportion, where it just says the proportion in the poll. Now, D, we actually already know. We know that the proportion in the poll is 0.66, and I'll go over that with you on the next question, how I know that. So we actually know the sample statistic. That's not what we're trying to estimate. We're trying to estimate the parameter in context. So that's the difference between C and D. C is the correct answer. Now on to what is the point estimate that was used to construct this interval, and what is the margin of error? So I created this little interval from A to B, which matches the problem in our work. It starts from 0.63 to 0.69. And I put a point in here, PE, which I can move around, and that stands for the point estimate. So our point estimate, we know that our range of values could be anywhere from A to B. So if you had to guess, does it make sense to be more on one side or the other? Or does it make more sense to be in the exact middle? Most people would put us in the exact middle between the 2 points. And how do we do that? We find the midpoint or the average of the two endpoints. So the midpoint we can calculate by taking the lower limit and adding the upper limit and dividing by 2. That's also averaging the 2 points. We have 0.63 plus 0.69. We get 0.66. And then so if we're trying to figure out now the margin of error, so we see that A, B, C, and E all have 0.66. By the way, it is not A because we're dealing with a proportion. A is a sample mean, not a sample proportion. You're probably going, well, but they're not that different. Well, the formulas for standard deviation are a little different, all right? And then this yellow and green section that I have highlighted here, this is your margin of error. So if we look at the left side, the margin of error is going to be the point estimate minus your lower limit, and we get 0.03. Let's do the same thing on the top side. It's going to be your upper limit minus your point estimate, and you get 0.03 again. It should not, you don't have to calculate it twice. Doing just one side is enough. So we can see now that the correct answer has to have a margin of error of 0.03, and it really needs to be a proportion for a sample. And your choice answer is B. Number 3, use the confidence interval to evaluate the reporter's claim. So they're basically, if you look at the solutions, we're looking at plausibility that more than or less than 2/3 of adults are in the interval. So looking, first of all, let's go ahead and how do we determine plausibility? Well, if you look at the third page of your H1 notes, concluding when a parameter is not likely to have a certain value. If you're given a possible value for a parameter, you can determine if it is plausible if it lies within your interval. So if it's in your interval, it's plausible. If it's outside your interval, then you have sufficient evidence that it's not plausible. It's still possible, but just not likely, not plausible. There's a difference between those two words, plausible and possible. So we're going to go back And we're looking at 2/3. Is 2/3 in our interval? 2/3 is 0.667. So because 2/3 equals 0.667, it is included in this interval. It is plausible that more than 2/3 of U.S. adults favor such an amendment. All right, let's see. Part B. So because 2/3 and values greater than 2/3 are in this interval. So see, this one only says 2/3 and it doesn't say value in the interval. It is plausible that more than 2/3 of the populations favors such an amendment. Now here's the problem. This one says there is convincing evidence that more than 2/3 of the U.S. adults favor such an amendment. No. If you go back, we only have convincing evidence for that it's not plausible. We don't have evidence that it's plausible. We only get convincing evidence that it's not plausible. You're going, what? Well, if it's in the interval, it's plausible. But so that's kind of our assumption going in, that, oh, okay, these are the possible values. And then we can change our mind. Oh, that's not likely. That's when we have the convincing evidence. So you'll get used to it as we get further. 95% of the time, there will be more than 2/3 of U.S. adults in favor of such an amendment because 0.95 is greater than 0.667. The reporter's claim is correct. Now, this is actually about confidence level, not interpreting the interval. So you can say if 2/3, actually this is completely false, see. Because the value and values less are in this interval, it is plausible that 2/3 of the population favor such an amendment. There is convincing evidence that more than 2/3 of the U.S. adults favor such an amendment. Again, we're in the interval, so we're not really finding evidence. D is not correct. Let's look at E. Because the value is in the interval, it is plausible that 2/3 or less of the population favor such an amendment. Thus, there is not convincing evidence that more than 2/3 of the U.S. adult favor such an amendment. So we don't really have convincing evidence. Our values are in the interval, so it's not surprising. We find convincing evidence when our values are outside of the interval. E is the correct answer. Okay. And that's part of the reason this unit is a bit challenging, and the units to come. What would happen to the length of the interval if the confidence level were increased to 99%? Well, if you want to be more confident that you caught the true value, you widen your net, and that means your interval would increase. So number 4, pretty straightforward. C is the correct answer. Number 5, how would the width of a 95% confidence interval based on a sample size 4 times as large compared to the original interval, assuming the sample proportion remained the same? So remember, the interval, this is our width. So you have your statistic, usually your mean, right? And you take your critical value, C star, and times your standard error. Well, if we're still doing a 95% confidence interval, the Z star is the same. It's going to be 1.96 because it's 95% confidence. All right, we're doing proportion, so that's good. And you're like, well, does that matter? Later, another unit. All right. So let's go ahead and look at the other part. So this is standard deviation, but since we're doing an interval, it's very similar. I guess I could have thrown up the standard error formula, which means we're using the sample proportion, by the way. But again, next lesson, all right? So, but the main idea is that n is in the square root. So if we quadruple the sample size, right, here's sigma for my p hat. I would have 4n instead of n, and I can pull that out. It's 1/4, square root of 1/4 times my original standard deviation, or 1/2 times my original standard deviation. So the length of this interval, this part goes in here. This margin of error is going to be half as big because this value is the same and this value is half as big. So my interval would be half as wide. Number 6. The news article goes on to say the theoretical errors do not take into account additional errors resulting from various practical difficulties in taking any survey of public opinion. Select, and by the way, it does say any survey. Select all practical difficulties that may cause errors, which are not included in the 3% percentage point margin of error. So that's an important part. Notice it says not included in margin of error. So you got non-response. Yeah, frequently an issue. True. 2, random sampling always occurs. So it says different random samples will produce different results because these different people are being surveyed. Yeah, that's true, but that's actually included in the margin of error. That's the whole point, all right? Number 3, people might answer yes. It's not obvious, but it's definitely possible. You know, they might feel pressured, response bias, to say yes. So this is true because which are all practical difficulties. And then number 4, we randomly sampled U.S. adults. We're not interested in people who don't live in the U.S. So number 4 is not an issue because it's not relevant to the question they were trying to ask, was which would be U.S. adults, because those are the only ones voting on the constitutional amendment. So 1 and 3 are true. Number 7, a confidence interval estimate is determined from the GPAs of a simple random sample of n students. All other things being equal, which of the following will result in a smaller margin of error? So again, remember the confidence interval, the margin of error is this piece right here, the critical value times the standard error of the statistic. So a smaller confidence level means that you have a smaller critical value. So this value would be a smaller margin of error. So we're going to say it's probably A. A is true. A larger standard deviation would increase the margin of error, right? They could also say standard error, by the way. And so B is false. A smaller sample size also increases the standard deviation, so that's false. Population size does not affect standard error, all right? The only reason it might be an issue is if you broke the 10% rule, but that's more in the accuracy of the calculation of this value than anything else. A smaller sample mean also does not affect the standard error. It's the mean is not included in that calculation, so E is false. So the correct answer is A. In general, how does doubling the sample size change the confidence interval size? Well, I'm going to make up some numbers to make this easier. There's no numbers here, so I can just make up my own example. So let's pretend that, so we have our sampling for the distribution of means is the sigma for that is equal to the sigma over the sample size. And I'm just doing a sample size of 20, all right? I'm not too worried about things being perfect. So we have 3 equals, and I'm setting sigma of x bar as 3, right? So I'm just making up some value, and I solve, okay? And I find, oh, sigma for x for the population is 3 over square root of 20. Now let's go see what happens to the, if I double the sample size. So now I have sigma of x bar. And again, you're asking me, where'd you come up with 3? Where'd you come up with 20? Where'd you come up with 40? I just made some numbers up, all right? And part of the reason I made up this number, I could have made up the other number. I just wanted a nice comparison between the standard deviation for this sample size compared to the one we're going to do here, all right? So this is looking the same, but it's my new one, all right? So now I know the population standard deviation is 3 times square root of 20. If I put that over and simplify, rationalizing, this is some ugly math, I know. Square root of 2 times square root of 20 is square root of 40, all right? And then I get sigma of x bar equals 3 over square root of 2 when I have a sample size of 40. So, and if I double again, let's go ahead and look at what happens now. We have a sample size of 80, all right? And then I go ahead and plug in and simplify, and I get 3 halves. So it went from 3 to 3 over square root of 2 to 3 over 2, all right? And so you can see every time it's like I'm dividing by square root of 2. And what is square root of 2? It's 1.414. So ideally, you should know, just straight off the top of your head, that increasing sample size divides your original standard deviation by the factor that you did to whatever the sample size. In this case, doubling by the square root of that. So if we're doubling, that's square root of 2, and the answer is 1.414. It's the same thing as dividing the interval size by 1.414. Number 9, suppose 25, 30 is a 90% confidence interval estimate for a population mean mu. This means that we estimate mu to be from 25 to 30. Which of the following are true statements? So there's a 0.9 probability that the sample mean is between 25 and 30. No, that's a confidence level, all right? So let's talk about confidence level, and that's from the blurb of the H1 notes, okay? If you use a C% confidence intervals often, about C% of your intervals will capture the true parameter. So let's look at the rest of these. 90% of the sample values are between 25 and 30. No. There's a 0.90 probability. No. By the way, your mean is a fixed value, the true mean, not your sample mean, your true mean. It has just one value, all right? And we mark it in the center of our little graph. It does not move around. It does not have a probability, okay? If 100 random samples of the given size are picked, and 90% confidence interval estimate is calculated from each, then mu will be in 90 of the resulting intervals. Well, that's 100, right? And it says will be in, you're not actually, and it says exactly 90 intervals. There are a couple issues with D. So let's go on to E. If 90% confidence intervals are calculated from all possible samples of the given size, mu, the population mean, will be in 90% of these intervals, all right? So that one's a little closer to the blurb. Go ahead. This should go on your cheat card. This is something you are expected to understand to interpret. So E is the correct answer. Problem 10, still waiting for the server? How does your web browser get a file from the internet? Your computer sends a request for the file to a web server, and the web server sends back a response. Let y equal the amount of time in seconds after the start of an hour at which a randomly selected request is received by a particular web server. The probability of y can be modeled by a uniform density curve on the interval from 0 to 3600 seconds. Define the random variable w, which is y divided by 60. What does w represent? So w equals y divided by 60, so it converts seconds to minutes. And there's no reason to think we have a uniform density curve for the original function. All we're doing is just changing the values, right? So it should still be a uniform density curve. Oh, I'm jumping ahead. But let's go ahead and say, what does w represent? It's the amount of time in minutes instead of seconds after the start of an hour at which a randomly selected request is received by a particular web server. So your answer is A. Now, what distribution does it have? First of all, they told us already that it's a uniform density curve, but even if they didn't, there's no reason to think one part of the hour is more popular than the other. So we're not dealing with normal density curves. It's got to be a uniform, right? And we're dealing in minutes, not hours. So let's make sure we get the right units, and it's D. Number 12. The number of calories in a 1 ounce serving of a certain breakfast cereal is a random variable with mean 110 and standard deviation 10. The number of calories in a cup of whole milk is a random variable with mean 140 and standard deviation 12. For breakfast, you eat 1 ounce of the cereal with a half cup of whole milk. Let T be the random variable that represents the total number of calories in this breakfast. What is the standard deviation of T? Now, I actually use the word instead of T, but that's fine. So total calories equals 1 times cereal plus 0.5 times milk. Now, because these are two completely different things, right? Two samples that we'll be doing, one of cereal, one of milk, you can't do them together. Then we have to work in variance, not standard deviation. So variance of T, or total calories, equals variance of your cereal plus variance of your milk. Well, remember, variance is just standard deviation squared. So for the cereal, it's just 10. Now, since we're only doing a half cup of milk, I can take that 12 and divide it or multiply it by 0.5 and then square it. Just make sure you do that first. Now, if there was some sort of plus on there, remember additive constant in here, we would tend to ignore that for variance, okay? So we end up with 10 squared plus 6 squared, 136. Take the square root of that, and our answer is 11.66. Number 13, another one. Lamar and Harish run a 2-person lawn care service. They've been caring for Mr. Johnson's very large lawn for several years. They have found that the time L it takes Lamar to mow the lawn on a randomly selected day is approximately normally distributed, with a mean of 105 minutes and a standard deviation of 10 minutes. The time H it takes Harish to use the edger and string trimmer on a randomly selected day is approximately normally distributed, with a mean of 98 minutes and a standard deviation of 15 minutes. Assume that L and H are independent random variables, very important here. What is the probability that Lamar and Harish finish their jobs within 5 minutes of each other on a randomly selected day? So if these are independent, then I can actually combine them using the rules. So this is like problem 12 on steroids. So not only do I have to find my mean, well, really my standard deviation plus my mean, I also have to calculate a probability with it. So we have the difference is L minus H, and they're within 5 minutes of each other. So you could have from -5, so perhaps H is faster than L that day, or H is slower than L. So -5 to 5, that would be within 5 minutes of being the same, right? Now I find my new mean, and I can just subtract them, and I get 7. Finding the variance. Remember, we have to, now you're probably going, but wait, you're subtracting here. We always add variances, even if there's a subtraction there. So we know standard deviation for L and for H, right? So we just need to square those standard deviations to get the variance for the transformed variable, and then take the square root of that to find the standard deviation. Now, okay, now we can answer the question. We're trying to figure out this, right? So that means we're going to use normal CDF. Lower is -5, upper is 5, mean is 7, and SD is 18.03. And let's go ahead and get some more practice on our calculator. Okay, so we're going to use the calculator to do normal CDF, which you should be a pro at by now. So we're going second distribution. There's normal CDF number 2, and our lower is -5. So I'll hit, make sure you hit the negative, not the minus. Our upper is 5, and our mean is 7, and the standard deviation is 18.03. So wow, that's pretty high. And we get 0.20299. So there's your answer, 0.2030, which is basically what that rounds to. Number 14, a random sample of golf scores give the following summary statistics. Sample size is 20, mean is 84.5, standard deviation is 11.5, and then we have the 5-number summary. What can be said about the number of outliers? So actually I can ignore X bar and standard deviation. That has nothing to do with the calculation generally. And we have to remember that IQR, we're going to need IQR equals Q3 minus Q1. So 91 minus 78 is 13. And then if I want to find low outliers, then I take Q1 and I subtract 1.5 IQR. And so I get 58.5. That's below the min that we already have. So we have no low outliers. Let's check high outliers. So we take Q3 plus 1.5 times the IQR, and we get 110.5. Well, our max is 112. Now, could there be 2 or 3 or outliers? Possible. All right, remember we do have a sample size of 20, so we know that it cannot be more than 5 outliers, all right? So, because, you want half your data points in the middle, that would be in the middle 10, and then you have another 10, another 5 on each end. But we do know that there is at least one, because we do know we have this value 112, so your correct answer is D, at least one outlier. Number 15, which of the following statements is incorrect? So let's evaluate these one by one. So the first one says the larger the sample, the larger the spread in the sampling distribution. So you frequently want to look at this. Remember, standard deviation or error always goes down with larger sample sizes by the square root of n, all right? So, or the factor that you double it or triple it or whatever. So A is incorrect. B, provided that the population size is significantly greater than the sample size, the spread of a sampling distribution is about the same no matter what the population size. So this is the 10% condition. As long as we're not too big a sample size, then yeah, the spread of the sampling distribution is about the same. So this is a 10% condition. All right, correct. Part C. Bias has to do with center, not spread of sampling distribution. I wonder why there's a question mark there. All right. Yes, random sampling gives a good estimate of the mean. This is why we random sample, is to minimize bias and to make sure we have the correct estimate of center. Sampling distribution, sample distribution, and sampling distribution refer to different things. That's actually correct. A sample distribution shows the individual data points from a sample. A sampling distribution shows all possible means for a given sample size. Actually, you know, if I were you, I might consider making that in my little 3x5 card. That is a true thing, and it's an easy thing to mess up, all right? And then E is correct because as n approaches n, we include more and more of the population. So the distribution of the sample, we're not talking sampling, sample, is going to look a lot more like the population. All right. Last, so the larger the sample, the larger the spread in the sampling distribution is incorrect. The answer is A on 15. Last but not least, number 16, a food judge is given an assignment to choose and sample the food at 52 out of over 20,000 New York City restaurants. She has an assistant list all restaurants whose names begin with A, assigns each a number, and uses a random number generator to pick 2 of these numbers and thus 2 restaurants. She proceeds to use the same procedure for each letter of the alphabet and combines the result into a group of 52. Which of the following is a true statement? Her procedure makes use of chance. That is true. All right. Feels like we've answered this question before, but in a different context. All right. B, her procedure results in a simple random sample. No, because they sample the alphabet separately. They're doing multiple samples, not simple random sample. Each restaurant in New York City has an equal probability of being selected. Well, I think we can go ahead and answer C and D at the same time. The restaurant Moosewood probably has a higher probability of being selected than the restaurant Xander. Well, C and D are not true. There may be more restaurants starting with X than M, or there may be more starting with M than X. The problem with D is that it says Moosewood does have a higher probability. I don't know. Maybe it's popular to name your restaurant, so they start with an X. I have no idea, so I cannot make D. D is tempting to say it's true, but it's not. E, this is an example of a systematic sample. No, sampling every 100th restaurant, or every probably 400th roughly to get that right, would be systematic. So E is incorrect. The only true statement is A.